Well, welcome everybody to today's Managing Heat Stress in Cotton webinar brought to you by CottonInfo. Thank you for joining us this afternoon as we explore how growers can better understand, prepare for and respond to extreme heat conditions. And we've certainly been experiencing those over the last few weeks. We're going to be covering off on heat waves, the tools for monitoring heat, impacts of high temperatures on crop physiology, managing cotton when we experience these hot periods, and we'll finish with a Q&A panel. So we're joined here today by some fantastic researchers with a wealth of experience on this topic, and that includes John Welsh, our CottonInfo Climate Tech Lead and Director of Ag Econ, and three CSIRO research scientists. We have Warren Conaty, Katie Broughton and Sandra Williams, all based in Narrabri. So with no further ado, I would like to hand over to John Welsh. Thank you, John.
Thanks, Janelle, and welcome everyone. Heat and summer. This is something we haven't seen this decade much. We've had 4.5 La Niñas, or virtually, since 2020. So heat is something that we experience quite often from sort of 2013 through to 2019. But this year it's returned. And what we'll be discussing pre-season, using the seasonal forecast to try and anticipate really hot growing season summers. In season, what do we look at then? The heat wave modelling as well. There's a couple of really good tools, and just tactically what we can do, week by week, and just share some research with you on what's been done in the past and what else we're looking at this stage on this topic. So just pre-season, during planting and water budgeting, the moisture manager, which comes out every month and more frequently in planting season as well, every fortnight, we do an interim report as well. But just from a seasonal point of view, I've just shared the October forecast there on the left side, and you can see there 2 of the 6 or 7 models there were showing a warmer than average 3 months from October, so November, December, January. The map on the right hand of your screen is a month later, and that's the IRI model, so the US Columbia University model that includes a bunch of North American science research agencies, is showing a shift from a month before to showing quite a favoured warmer tercile temperature prediction for the summer. So that outlook was published in the middle of November for December, January, February. And that's a really good model. That's my go-to. And certainly that seems to have shaped up as per observations with quite a hot January, certainly baking a lot of the landscape here in Eastern Australia. So when it comes to heat, there are things we can look at during in-season, so we are aware that the growing season could be hotter than normal. Ocean indicators are really useful as a predictive tool, simply because they're low frequency. So what that means is they move quite slowly. Scientists track these with ocean buoys going down with telemetry quite a way into the depths of the ocean to try and understand where the warm water and where the cold currents are. So looking at the oceans can give us some insights as to when the heat is coming. And just sharing some research that's been done in the past, explaining all these colours and shadings. We've got 3-month rolling window. You'll see there March, April, May starting at the top, and that's in the Gundawindi location. So wherever you see numbers, they're significant at 95% confidence intervals, and the darker the shading, the stronger the connection with those ocean indicators. So if we look in the Western Pacific at the Niño 4 indice, we've got quite a strong correlation on the border rivers there for September, October, November with what's going on in the Pacific. So the take home here, I've just got some text there in the middle of the screen. Basically, it's fairly consistent, and heat is one thing, but crop ETO drives irrigation demand, plant water demand. And the take home here is that crop ETO tends to be aligned with El Nino or La Nina. So when you have a La Nina summer that's quite a strong event, you tend to get cooler conditions or lower plant water demand or ETO. And then having a look at Trangie as well, there's some different relationships there, quite strong through the early part of summer with the black circle. And then in the Indian Ocean, which is the DMI, right down the bottom here, the fourth column along, there's some good connection as well with basically heat, wind, and irradiance as well with the dipole mode index. So it's just kind of good to know those relationships. There is a really weak surge of La Nina just decaying at the moment. We sort of reached threshold for a short period of time, so it's a little bit unusual to see that hot forecast back in October, November for a hot summer with that La Nina condition. So it is a little bit against the trend of this research and what we've seen in the past. So in season, what actually is a heat wave? It's not just about getting one hot day. The scientists have measured heat waves with respect to not just the maximum, but also the minimum temperatures, because the landscape just doesn't really get, and the plants don't get a chance to cool down when you have hot nights. And that's one of the interesting parameters about measuring heat waves, is not just about hot days and cooler nights. It's about getting the dual impact of hot days and hot nights as well. So that's the usual definition of a heat wave as the Bureau views it, when it gets unusually hot over 3 days and about the minimum temperatures being, in the top tercile as well. How do we track heat waves? This heat wave tool is published on the Bureau's website. For those that don't know, the link's down the bottom of your page there. We do also feature this in the sign tab in the moisture manager as well. And this is actually going out 7 days now. It only used to go out 3 or 4 days at a time, but it's really useful to play that loop. And you can just see there, I've extracted this image from yesterday, and there is some low intensity heat predicted for central eastern areas where cotton's grown there in northern New South Wales, etc., for Sunday, and then that dissipates post that. So a very different view from 10 days ago at the end of January, when we certainly had some deep red extreme colours right through the interior of the continent, plus Western New South Wales and Southern Queensland, and right across Victoria as well. So this is updated regularly. It's certainly should be a go-to in your favourites for irrigators, scheduling water and just trying to be across, being on top of these heat waves and keeping the crop as cool as you can. So just some research has done in the past. It's probably quite well hidden research. We published a paper with University of New South Wales a couple of years ago, and we used 30 years of CSD ambassador site data to categorise what was going on with yield in an irrigation setting and a dryland situation. And we categorised using deciles, so a really wet period and then different combinations of temperatures in 2 locations. These are both irrigated. So what you can basically see from these 2 charts is that cotton, when it's irrigated, handles heat remarkably well in terms of its yield. You'll see those really hot years where we've hit, the 10th percentile of heat years. We've seen the crop withstand that heat reasonably well, and even when you have average rain and really hot conditions, which is the asterisk here, sort of 2/3 along the way this axis, the yields have stood up not too bad in both of those locations. Whereas if we look at, as a contrast, cotton has withstood those extreme events far better than the really cold, wet extremes at the other end of the spectrum. So there's lots of detail in that paper, how we categorise the conditions, the growing season conditions, and then taking a quick look at dryland and the impacts on yield. And one would say, yeah, this is pretty elementary. But what we've seen in a dryland setting is that the heat really does towel up the crops substantially when you have extreme heat, and obviously dry generally seems to be coupled with that. Although there are occasions here where we've had really hot conditions at Ballatta, for example, and average rainfall, and they've been fantastic years where we've hit that mid-tercile rain band for December, January, February, and the crops withstood those hot conditions quite well. And coming down to Cecil Plains here on the bottom chart, not so well when they've had really hot temperatures. The best years on the downs have really been when you have basically average temperature and average rainfall. So that's some research that you may or may not have seen. And incoming, we have some new research just in preliminary stages. The project has been awarded by the Future Drought Fund. What we've suspected in dryland areas with the climate during that paper with University of New South Wales, during that research, is that when we see a wet phase of the Indian Ocean dipole occur in our spring, that tends to flip over into a dry, hot summer, which kind of may explain to some degree the 25-26 growing season we're in now. That Indian Ocean dipole influence occurred in the spring, and if we can better understand that relationship with the dryland cotton areas, I think that'll definitely help management if we can see these events coming and avoid the case where you have failed dryland crops in these key growing areas. So that's coming through the pipeline. We're in a situation now, we're just about to complete contracts and advertise for a research fellow to undertake that 2-year study. So watch this space, and we'll certainly be in touch with Janelle as those results come forward. And that's it from me. There's plenty more I can discuss, including Madden Julian oscillation and those phases, but probably depths are for another day. But over to you.
Thanks very much, John. We've just got one question. Welsh, did you split the dryland data up by planting date, e.g. October plant versus November plant in your study?
No, it was a fairly coarse look. Most of the horsepower in that research went into defining the climate variables into deciles. So we had a whole bunch of different deciles for rainfall and temperature, and that was kind of the main focus. That's actually another unique question, really. I mean, I think that the cutoff for that data was 2020. So we've had another 5 or 6 years of data collection since then. So that would be a really interesting thing, and I'll see whether we can address that in the upcoming study. I'll make a note of that. So thank you.
Well, thank you very much, John. We're going to move on now, looking at what the high temperatures or heat stress are actually doing to the cotton plant and how the cotton plant's responding. So I'll hand over to Warren, Katie and Sandra, and it's a bit of a tag team through the following presentation. Thanks, guys.
Yeah, thanks, Janelle. I get the privilege of kicking off from the CSIRO team, and then I'll hand over to Katie and Sandra. It's a great pleasure to share some of our work that we've done and some of our understanding of cotton physiology in response to heat stress. I'm going to start talking about the physiological responses to heat stress and what that means for the plant. And then Katie is going to come in and talk about the actual impact that has on the crop and ways that you can mitigate that or deal with the heat. So there are just a couple of numbers to sort of share with you. Cotton is a thermally driven plant. So its growth and development can be tracked through thermal time. And everyone knows that. We call them day degrees. And it's no surprise that the 1532 number in the new way to calculating day degrees, those numbers aren't random. 15 or 15.6 to be precise is the base temperature. So that's where really growth and development stops or doesn't really happen much at all. It completely ceases at 11 degrees. And then the 32 is sort of indication of the optimum temperature. So the optimum ambient temperature or air temperature that we feel for cotton to grow in would be 32 degrees during the day. The cotton plants will experience a level of heat stress once you get to about 35 degrees. And then it's categorized as more extreme heat stress once you reach that 40-degree mark. So those are just a few numbers to keep in mind when you're thinking about the ambient or the air temperature during the daytime. And look, the reason that this is important is that and you can see from this sort of seminal figure that Janelle actually recently shared in an update, is around what air temperature or ambient temperature, how that impacts cotton growth and development. And you can see based on those numbers that we were just talking about a moment ago, down at 15 to 11 degrees, there's very little growth or development. You peak up around that 32 degrees. And once you start to get past 35 and moving up to 40 degrees, your rate of growth and development starts to decline. And the increase from the suboptimum is quite rapid. And then you have this sort of period of the peak around that peak of 32. And then after you get to that 35, you start to have an impact of heat stress and all of the things that people will have experienced, reduced growth rate, cavitation or shedding. The cavitation is where the bolls freeze on the plant. You can have impacts on pollen and you end up with the parrot beak bolls. And then, you also get impacts of yield and fiber quality as well. And you see that all happening after the crop gets above that sort of 35 to 40 degrees. To go into a little bit more detail on that, we really need to start to think about photosynthesis and respiration. And these are really the core ways that the plant is productive, or the productivity of the plant. So photosynthesis is really converting carbon dioxide, water and sunlight into carbohydrates or glucose and oxygen. And really that's how the plant fixes its energy. And, this is sort of, high school science type stuff, but it's really important to keep that in mind. And then the opposite of that is respiration, which is where basically you just flip that sort of equation around, where the plant uses its stored carbohydrates or glucose with oxygen to convert back to carbon dioxide, water, and actually use that stored glucose and convert it into energy. Now, photosynthesis happens in the daytime only, but respiration can happen in the day and the night. And keeping those two processes in mind, I'll just go through a little bit more around what the impacts of temperature is on those processes. The other thing that is important to keep in mind is just a little bit of anatomy of the plant. So when you sort of look at a cross-section of the leaf, you can see all of these different types of cells. And the important one that I want people to recognize, or there's two, is the guard cells. And we also call those the stomata. And that's the pores where the CO2 can enter the leaf to be able to fix carbohydrates and for photosynthesis to occur. And it's also where water leaves the plant. So water that's pumped from the root system up through the vascular system or the pipework of the plant and comes out on the surface of the leaf. As the CO2 comes in, water will come out because of the gradient of higher humidity inside to the leaf to a lower humidity outside of the leaf. And that's really important for transpirational cooling. And then the CO2 comes into the cellular parts of the plant, into the mesophyll. And the palisade mesophyll is where most of the photosynthesis occurs. And so those are the sort of the two really important things, particularly the stomata, which are the guard cells that I want to just touch on today. So the reason that this is important is because even though the optimum ambient temperature that cotton likes to grow at is 32 degrees, the optimum plant temperature is actually 28 degrees. And this is sort of substantially lower the plant temperature. So the equivalent would be our internal body temperature. We want that to be around 37 degrees. And, our optimum air temperature, well, for me, it might be, 23 degrees or 24 degrees, and someone might be 26 or 28 degrees. But it's really what your body wants to be at. So for the plant temperature, it's 28 degrees. But the ambient temperature or the air temperature that it is experiencing is most optimum at 32 degrees. And the reason that this is important is that transpiration is the key to keeping the plant at that 28 degree or as close to that 28 degree mark as possible. And actually work from my PhD sort of, really shows that the productivity of the plant, so the yield from the gross productivity of yield right the way through to photosynthesis is really peaks when the plant spends more of its time at 28 degrees. And the key to keeping the plant at 28 degrees, particularly in the context of heat stress, is water availability. And when you have a very hot day with a very low humidity, which means the air is dry, you can get a lot of movement of water from the surface of the leaf out of those stomata pores and out into the environment, creating evaporative cooling. And it essentially works exactly the same as your evaporative cooler on the roof of your house works. You're pumping water over a surface, it evaporates and cools the air. And essentially the same thing happens. The stomata, the pores open if the plant has enough water. That allows carbon dioxide to come in, so you get a high rate of photosynthesis and productivity. But as a result of that, you also get a high rate of water coming out of the leaf, and it maintains high transpiration, which means the plant can cool itself. So when you have high water availability, you have a lower plant temperature, the plant will try and maintain its temperature around that 28 degrees, and that means you have a lower potential for heat stress. Obviously, the opposite of this is sort of true when you have low water availability. So at that point, the stomata will close and there's no longer a way for carbon dioxide to get into the plant. And that's important because you're no longer productive, you're no longer fixing carbon, you're no longer creating yield. It also means that you don't have a route for transpiration to occur, so there's no transpirational cooling of your plant. And the plant itself, or the canopy temperature, will increase, and then your potential for heat stress also increases. And the plant does this to avoid complete desiccation. So it stops using water to avoid using all of its water up. And it's basically a survival thing. Now, in an irrigated sense, you can obviously apply water to manage that. In a dryland situation, it's much more difficult to do anything about it. But it's important to know how the plant responds in that scenario. This figure here is just to further emphasize that when you're looking at the plant temperature or the leaf temperature and you're relating that to photosynthesis, you can really see that sort of 28, 29, 30 degree sort of mark is really where we see a peak in photosynthesis. And without photosynthesis, you don't have carbon being fixed. And without that, you don't have the ability to produce yield. And really, the important thing is, so long as you have water availability, a plant can cool its internal or its plant temperature by around 10 degrees below the ambient, provided that there's low humidity and provided that there's access to the water. And Katie will go into a little bit more detail around some of that in a moment. So what about night temperatures? John mentioned that they're very important, and it's important in the definition of a heat wave, but it's also really important in the context of cotton and how it grows and its productivity. So the optimum values for night temperatures around that 18 to sort of 20 degrees, and a high night temperature as classed for cotton is 25 degrees. And the reason that high night temperatures are bad is because remember how I mentioned about photosynthesis, which is the fixing of carbon. Respiration is sort of the using that stored carbon and turning that back into energy. And this happens in the day and the night. Usually it's around 30%, but it can be up to about 60% of your photosynthesis can be used for respiration. Now, respiration in itself is not a bad thing. And there's two processes for respiration. There's growth respiration, which is when the plant is growing. It's obviously producing and needing to grow and produce more bits of the plant, really, like cells and all sorts of things. And that's the energy used to create those. And then there's maintenance respiration, which is where the plant basically does its housekeeping, where it fixes proteins and it fixes lipids and adds lipids and things into the cells. I guess it's a maintenance or a kind of fixing to make sure that the plant can remain functional. The reason that night temperatures are really important is that high night temperatures really increase the amount of carbon used for maintenance respiration overnight. And that essentially what that means, I like to draw the analogy of the plant on a cooler night of that 18 to 20 degrees sort of gets up the next day, starts firing and hasn't used as much of its stored carbon. Whereas a plant that's had a hot night for 25 or above, wakes up, and it's a bit like after waking up with a bit of a hangover. You're sort of on the back foot. You've used all of this sort of stored carbon that you had, and you've got to work harder to get back to be able to start fixing carbon and being productive again. And then the final thing that I wanted to talk about, the reason why I'm talking about photosynthesis so much is that the source sink dynamics is what really is important in terms of driving the impacts of the photochemistry on the plant and the crop that we see in terms of impacts of like shedding and cavitation or bowl freezing and those sorts of things. So the source is the carbon dynamics or the supply of the carbohydrate, and the sink is the demand or the fruiting dynamics. And when supply is greater than demand, which is on the left-hand side of the slide, it's a heavier, so you've got more supply than demand, is when the plant is in a growth phase. And the opposite happens when demand is higher than supply. And basically what the response is a shedding phase, a fruit shedding phase. And so what that means is that under that scenario, where you have a heat stress event and you're producing less photoassimilates or less carbon or less glucose essentially from the plant, your source sink dynamics can be upset so that the supply no longer can meet the demand. And that's why we see shedding and cavitation, and is also why we see impacts on pollen viability and pollen amounts. With all of that sort of background in mind, I'll pass over to Katie, who's going to talk through some of the crop impacts and management and then what we've actually seen this season.
Great, thank you. And thanks for setting up some of that background, Warren. So if we're thinking about some of the impacts of what we might be seeing in a heat stress event, because of that sort of source sink dynamic that Warren was talking about, we can see shedding and cavitation of young bolls. This large photo that you can see is actually a photo that we took a couple of years ago when I was doing some of the climate chamber work, and inside the chambers we were getting much warmer temperatures, and we saw quite a bit of shedding and cavitation of the young bolls when they experienced heat stress. We can also see with the heat stress that you can get some low pollination, and Warren's done some of the work around understanding pollen and how that is affected by heat, and we can sometimes sort of see low pollination leading to parrot beaking. However, there is quite a bit of pollen, and so that's sort of like more of a, when the heat stress is more sustained, that could be a larger problem. And then, so that's sort of in the developing bolls, and when the bolls get like a little bit bigger, some of the impacts of heat stress that we might see are things like short fibre and high micron air, when the plant's not being able to transpire enough and fill the fibre through that fibre elongation phase, and leading to the short fibre and high micron air, with some of the work that Mick's done around some critical bowl filling phases where there's higher temperature. You can see some effects on high micron air with the warmer average temperatures during those critical phases. And so I guess some of the things to keep in mind around these impacts is also depending on how long the heat stress lasts for. A shorter period is only going to affect a smaller number of bowls, whereas a more sustained heat stress will affect those bowls for a greater period. So what can we do to manage the effects of heat stress? And I guess with Warren touching on the importance of water, that if water is available and we can irrigate, then you'll see that often people will manage it by shortening up the irrigation periods. And that's just to make sure that the plant has the water available to be able to transpire, to be able to keep its temperature that bit cooler, and trying to maintain photosynthesis and transpiration during a heat stress event. Some other things that we might be considering is trying to eliminate any other stresses. So if we know that there's a heat stress event coming, we might reconsider some of our growth management, and particularly growth regulator use, and then waiting to see what the effect of the heat stress is, and then coming out of that. That's also going to depend on when the heat stress occurs. So yeah, how close to cutout we are, how much more season length we have to be able to grow the crop on, and if there's problems with retention, and yeah, considering how much season we're wanting to be able to continue growing bolls and trying to increase our yield, because the plant has an amazing ability to be able to compensate with some of those fruit losses that we might have throughout a heat stress event. So we're wanting to consider that and trying to eliminate stresses so that the plant can just focus on getting through that heat stress event. And I guess my final point on this slide is maybe not something that we can do much about right at this point in the season, but for future seasons, trying to set up the crop so that we have a deeper root system. And if we've got a deeper root system, we've got more access to water, and the plant and the crop has a better capacity to be able to be a bit more resilient in times of heat stress. And so the ways in which we might be able to do that is stretching irrigations when the air temperatures are cooler in the season, and we've got the capacity to be able to try and encourage those roots to search a little bit deeper in the profile. So yesterday I jumped onto the CSD degree calculator tool, and just thought it would be interesting to have a little bit of a look at some of the air temperatures across some of our regions, our cotton growing regions. So this is data from the start of January up until the first couple of days of February. The red are the maximum air temperatures for Griffith, Narrabri and Dalby, and the blue dots are the minimum, the nighttime minimum temperatures. And what you can also see that I've shown here is the red dashed line is that threshold that Warren was talking about earlier at the 35 degrees, where if we exceed that, then the plants might be starting to move into that slight stress sort of temperatures. And the blue dashed line is our 25-degree nighttime threshold that Warren mentioned, that being important about for respiration. So so just having, I guess, like a quick quick look is that we can see that sort of through early January, Griffith had had some quite a number of days where they exceeded that 35-degree threshold during the day, and a couple of instances where the nighttime temperatures exceeded the 25 degrees. So a little bit more heat in Griffith, sort of like beyond what we experienced last week. In Narrabri, we can see that actually throughout the beginning of January, we were just sort of tracking just above that sort of 35-degree threshold, and then got that heat on top of that late last week. But the nighttime temperatures only exceeded the 25 degrees, sort of, maybe once or twice. So the cool temperatures were cool nighttime temperatures probably helped the crop along despite those those higher daytime temperatures, allowing it to recover a little bit more with the respiration. And in Dalby, actually that looks like somewhere that I might like to have been this season. There hasn't been as many temperatures exceeding 35 degrees during the day, and by the looks of this, no nighttime temperatures that have exceeded the 25. So so that's just data that I had pulled from the CSD website, and was quite interested to have a look at where the temperatures that crops have been experiencing this season, and I guess in terms of this, also thinking about where we are in terms of how much growing season we have left in to be able to respond to those warmer temperatures that we experienced, certainly Griffith and Narrabri experienced early last week, and thinking about how much season we have left to grow the crop will help shape the management decisions for each region. These are some photos of our dryland trials up in Moree that we were at this morning, and Sandra, Greg and myself were there, and we were just having a little bit of a look and observing what we could see in our trial. So the photo on the left, they're actually some smaller plants. So this was a trial that was planted on the 6th of November. And being dryland crop, there's been plants that have germinated at sort of different stages. So on the left, we can see some younger plants. They don't have as high a bole load, and they had some younger fruit where we could see that it has shed. So the red circle is showing some of those fruit that have been shed on the ground. So smaller plants with smaller bolls. Also considering that those plants probably haven't had as deeper root penetration, and compared to on the right, we can see some of the plants that have germinated earlier in the season of that planting, and those plants were looking pretty. We thought they were looking pretty good. We searched. We found a few sites that had cavitated, which you can see with the circle, that red circle, but otherwise the plants were looking rather healthy. They were quite cool to the touch, indicating that they're transpiring well, not really sort of showing signs of water stress, and also, I guess, not having thrown a lot of fruit off at this point, indicating that they were able to maintain the supply that it requires to continue filling the bowls at this point in time. So that's what we saw this morning up in Moree, but I'm sure everyone's sort of seen various things at their own places. So I think that's me. And thank you very much. And hand over to Janelle.
Thank you very much, Katie. I really appreciate all of you in presenting here. Just a question for you, Katie, on the graphs that you put up with those air temperatures. So in effect, this season, we've been pretty lucky because the minimum temperature at night's been around that optimum. So it's actually had time to recover. That's right, through the season. So we're not eating into our stored carbohydrates the next day.
Yeah, I think that has probably helped the plant sort of cope with some of those higher daytime temperatures. Yeah, that the plant has been photosynthesizing well, and I guess that's probably where it's an important consideration as to whether we're comparing sort of an irrigated or dryland crop and how much water the plant has had access to transpire and cool its leaves down. Warren, do you have anything to add to that?
I don't think so. I think the only thing would be is from reports, I think a lot of irrigated crops have managed to get off fairly well in terms of the effect of this, because the temperatures were not as extreme. People were watering on time or getting timely water on, and with the lower humidity associated with this heat wave, it wasn't a humid heat wave. The plant can cool itself and maintain the temperatures back towards that optimum. So I think there has been fruit shedding, but that's also comes to that source sink demand as the plant reaches cutout as well. So, and that's luckier that the heat wave is later in January rather than early in January when you've still got effective flowers, or more effective flowers and more bulbs to set to get the yield that you're after.
No, for sure. Will high night temperatures cause smaller bolls?
I think my logic is that yes, because if you're using your carbon, more of your stored carbon for maintenance, respiration, you've got less carbon supplies to draw on to be able to fill those bowls. It depends on the degree of how hot the nights are and how sustained that is, and how much the stored carbohydrates and are lost or used by the plant for maintenance, respiration overnight. But yeah, ultimately, you want the plant to be in that optimum temperatures, ideally when we have no control over it. But and that's when the optimum conditions are optimum. You get more bigger bowls and better yield and all of those sorts of things. So it does, yes. It's a long way of saying yes.
And after a run of high temps, day and night, how many days to recover? That is, if another run of high temps hits within a couple of days. There's a lot of factors in that one.
There are a lot of factors in that.
Yeah, it's difficult to answer because we often simplify it in our minds that, today it was 45 degrees, right? But there is periods of the day where it's not 45 degrees, and there's periods of the day as the temperature is increasing that you're at the optimum as well. And it's the same as the night temperatures. There might be periods where it's hot, but other periods where it's not. And the plant is doing things at all of those times. So we simplify it down to, this was a 45-degree day and this was a day that had a high temperature. So you can think of the periods outside of the optimum is where you start to be impacted and the impacting the crop. But there are periods during the day where there's less impact or no impact, I guess, as well. In terms of how many days to recover, in my view, it all boils down to those source sink dynamics. So if you don't have enough photosynthesis or supply to be able to support bowls and you're losing them, so long as they're not bowls that are going to, or fruit that are going to go to yield, that's not a problem. But obviously there are many situations where that is. And I don't think it's about a recovery period, if that makes sense. It's about when that source sink dynamics are in balance and favoring growth and development of the and setting of those bowls, and then the development of those bowls. I don't know. What do you think, Katie and Sandra, if just throw you guys under the bus?
Yeah, and I guess if it's got the some of the factors around that we've already touched on around sort of how much water it has, I guess how high the heat temperature, like how high the heat stress event is, like the duration. I think that the plants sort of bounce back reasonably quickly in terms of the fact that they do have the photosynthesis and transpiration happening at those other periods in the day. And I think I don't think I have anything much more to add to what you succinctly put.
Thanks, guys. We'll move on to another question. We've actually got a fellow from overseas, and they're experiencing 45 degrees during the day and 38 overnight, and with losses of up to 70% of yield. So like they are certainly extremes. Now, heading back down south, cotton in the south is pushing cutout now. Small canopies have dropped more fruit in our runner 40s last week. How much does canopy size have on regulating temperature, or is it purely more assimilate supply to support bowls through the heat?
I think, again, they're all linked, because the bigger the canopy, the bigger the assimilate supply. The bigger the canopy, the bigger the plant, the bigger the root system, the bigger the bucket to be able to pump water. So obviously then, if you're in a situation where you can't keep water up to it, a bigger canopy is going to push the plant into heat stress as well. But obviously you need a big canopy and a big plant structure to be able to support the yields that we're after too. So they're all linked. The canopy size is a consequence of the photoassimilate supply.
Can I just add something there? Like the crop that Katie and I were looking at this morning, it was a little bit funny that you say that, because the larger canopy, the larger plants on this dryland cotton, I'm not talking about irrigated cotton, the root system must have been down like 1.80 m, like 2 meters, because it wasn't showing that many signs that it had been affected by heat stress, other than it's only had about 50 mils all season. So it cut out about probably 2 to 3 weeks ago. It was looking like it was done and dusted. But the younger, smaller canopy plants that had germinated a little bit later in December, even though they were small, and if you think about the source-sink relationship, they were small, but the root system must have been quite small, because it couldn't cope, and it had shed all the young fruit and had left just the couple of older bolls. So I don't know whether that's relative to the irrigated cotton that you're looking at down south, but today what we saw was definitely root system related more than anything.
Thanks, Sandra. We've got one here. Seems that the heat wave last week in the south coincided with cutout mepicot chloride timings. Should you go before the heat or after with cutout rates? So in terms of timing of your cutout mepicot applications, before or after the heat stress?
I think that's one for Katie and Sandra.
Yeah, no, I'm thinking it depends on whether you know that you're going to have, it depends on whether you've listened to John and taken note of whether there was a heat stress event coming, because you may not have needed to actually apply the cutout. It all depends on the crop. It really does. I know that for down south, you've only got a couple of days to your last effective flower. So the young fruit that you see now isn't really the squares that you see now is not going to make it into a picker basket. So you could have potentially held off the PICS application. Yeah, I don't know whether that actually answered the question or not. For the areas like here where your last effective flower is not until the last week in February, and for the crops, there's crops that have already cut out everywhere, and that was tracking towards cutout way before this heat stress event occurred. And I think it was from what I've seen, it's just really good boll loads, and a good boll load is your best growth regulator, as everyone knows. So if you're, and there's a question here, you know, what happens if it rains tomorrow? Your crop starts growing again. You're in Moree. Do you let it grow, or do you put a PIX application on now and cut it out? I think all depends on the district, but just take, for example, Moree, where your last effective flower is the last week in February. You know that it's that if you did have enough water and you did have enough nutrients, then it could potentially start growing again. But you would probably want to look at a good cutout rate of PIX at least 10 to 14 days before the last week in February. So for me, I would be looking at cutting it out next week, or looking at management strategies towards cutout probably next week. So you may not want to let it grow for that district. So it all depends on where you are. I don't know whether that answered the original question or not, but I certainly answered one of the questions on the chat, Janelle.
Thank you, Sandra. Is there any evidence to suggest that more closely, densely planted cotton can better withstand hotter temperatures, particularly later in the season when plants are larger and wider, versus, say, single skip configurations where there's more surface area exposed directly to the sun?
I don't know, to be honest. It's a good question. I guess the only thing I could say to that is that the ability for plants, particularly if you're talking about a skip configuration, you're probably more likely in a dry land scenario that the configuration or the plant type that has that allows the plant to access more water, have a bigger bucket to access the water, will be able to potentially mitigate heat stress a bit better. Yeah.
I agree. Janelle, was this more of a irrigated question or dry land?
Dry land.
Yeah, from what we saw today, definitely the plants that had plenty of room didn't seem to be affected at all. So, but there was no comparison because the crop that we were looking at today only has about 6 plants per metre on a metre and a half spacing. So it's got plenty of space to access a good bucket of water.
And I guess then you're sort of also thinking about some of your management in that around sort of, you know, if you've got stubble retention, that, you know, is also part of the water conservation management of a dry land system as well.
Linking to that, Janelle, I see that Bob had a question about planting date and does that help with management of heat? I think, yes, it does. And provided you get, obviously, it's all on the proviso that you get planting rains later in the season, back in November. It means that you shift your flowering window of your plant more towards those cooler conditions. So rather than in that peak of heat in January, more towards the end of January and the start of February, where historically we're more likely to have less higher temperatures. And so that is one way to manage heat stress in a dryland crop, and it all does depend on when you get that moisture for planting.
There's another question. Often, like in the morning, your minimum temperature might be 26 degrees, but it'll say it only feels like 22. Given the parameters used to calculate, is this a more appropriate value to use when looking at minimum temperature? So do you use the actual 26 degrees or the feel like temperature?
A good question. I don't know the exact answer, but basically what the feels like takes into account the humidity of the air and the movement of the air, so wind, and that basically it makes it feel like cooler than it actually is because there's more evaporation or coming off your skin through sweat or whatever, and more movement of the air to take that heat away. So probably the feels like has a stronger correlation to what the plant is feeling like, but I don't know whether there's been specific work done on that. But it's a good question. I don't know. Do you know, Katie or John? John probably has a better idea of how those feels like are calculated.
Yeah, the feels like is a basket of criteria, a little bit like crop ATO. So it takes, there's a weighting for wind and humidity, as you say, Warren, which isn't dissimilar crop ETO, which drives plant demand for water. So yeah, I think it's that midpoint between actual ETO calcs and the raw temperature.
Yeah, because if you've got a lower humidity and there's movement of air, the ability of the plant to cool itself through transpiration is much higher than if you've got a higher humidity and still air, because there's none of that air movement, and the gradient of humidity from the internal part of the leaf to the ambient or external to the leaf is higher, so it can draw water out in the low humidity.
And a final question here, because we are going to run out of time. Is there a significant difference being observed between current and new lines in terms of heat tolerance?
I guess I'd better try and answer that. I think that I don't think we would routinely assess that. Look, I'm not sure of the answer. It's got me on the back foot, that question. Whether there's a difference in the plant's ability to withstand. I can't see where the question is, Janelle.
It was just looking whether there was difference in heat tolerance between. Is there a significant differences being observed between current and new lines in terms of heat tolerance? So are there any new lines coming through that have some significant better heat tolerance?
I would say that we've looked in the breeding program at a number of different ways to assess heat tolerance and try and breed for that. We've looked at pollen viability, and we've realised that in our episodic heatwave events, the amount of pollen that the plant produces, retention isn't actually driven by pollen viability, it's driven by those source sink dynamics. So that was one way that we wanted to breed for heat stress tolerance. I guess one of the other things that will have one advantage of one variety of another is its level of determinancy. If you have a more indeterminate variety, it can basically grow and compensate faster than a more determinate variety after a heat stress event. So there's a number of different factors that you could take into account. I'd have to take a rain check on applying that to the current commercial varieties. They'd all be relatively similar, I would say. There may be specific differences across people have observed, but they might not be wholesale across the whole industry or across every scenario.
There's one question here. Have you looked at chronic heat stress events versus acute heat stress versus accumulated heat stress?
I think the way the plant responds is largely the same for it across those different events. The difference is that if you have a chronic heat stress scenario, you're going to continue losing fruit, and there's going to be less and less time for compensation. I do think that also the scenario that I can't remember who it was, that someone had said that from overseas that they're 45 degrees and like a very, very tough climate to be growing anything really. That would you'd have a different approach to management and also to breeding as well, because most of our heat waves are episodic, and most of them the crop cotton is indeterminate. It has a really good ability, as Katie mentioned, to compensate and set fruit again. Because what we found in some of the research that we've done is that plants can still cotton can still retain their bolls during a heat stress event. And it's not due to lack of pollen or anything like that, but then the bowl ends up becoming much smaller because there's a lack of carbon to fill that bowl if it isn't lost. And so one of the things is that once a bowl's about 8 days old or so, it won't be aborted. The plant will maintain that and keep that on its structure. But if you're favouring a plant that retains fruit during an episodic heat stress event, you might end up favouring a variety that keeps that fruit, but then you're going to have smaller bowls that are taking from that source sink dynamics that a demand, when actually it could turn out to be better to have setting fruit in more optimal conditions. I'm not sure whether that answers the question, but
question on fibre quality. When does it have its greatest impact, I guess, like early season, mid, late, in terms of these heat waves? And are there any strategies to mitigate high micron air in hot seasons?
I think that the biggest impact would be on when those bowls are developing. So if the heat stress impact is on is impacting the fibre, it will only be during the bolls that are developing at that phase during the heat stress event. And so the fibres form at different phases, and different aspects of the fibre or fibre properties form at different times. So at the start of the process is the fibre length or the cell elongation. And so during a heat stress event there, you might end up with shorter fibres, particularly if the plant can't maintain transpiration and can't keep its water balance up and remain turgor in the plant. But that's only during the early parts of the boll and the fibre development. Later in the development is more towards where the micronair occurs, impacts occur. And so if you think of when you've got your peak amount of bolls on your plant that are undergoing their development, it's going to be impacted by a heat stress event there in terms of quality, much more than at the very start or the very end of the season where you've only got 1 or 2 bolls that are undergoing those biological processes of the development of the fibre during those periods. So you get boll development sort of goes exponential for a while and then tails off when the plant kind of cuts out. And it's at that sort of peak of the rate of increase of bolls that would be where a heat stress event during that period would have the most impact on fibre quality, because there's the most bolls developing in that period of time. It's just basically on pure numbers.
So do you think there's any specific management strategies that we can put in place to limit high micronair in a hot season?
I don't know specific reactive management strategies beyond, managing the heat stress broadly through irrigation and those sorts of things. You could grow a variety that has a tendency to have a lower mic if available. You could, and if suitable for your environment, you could also, I guess, there's the altering of planting dates and those sorts of things to try and avoid when it's more likely to happen. But I think one of the things with heat stress is you sort of you get what you get, and you don't get upset, and you just kind of have to manage through it. And there's only so many levers that we have to be able to pull, I guess, particularly reactive levers. The main one is irrigating your crop to reduce that stress. The other ones are all pre-decision, pre-planting, setting your crop up to have a deeper rooting system, variety choice. They all happen before you're thinking about heat stress.
And is there a difference in transpiration and heat stress between the different leaf shapes? So if we're comparing your okra versus your normal leaf?
I don't think so. You get differences in light penetration into the canopy, and you get differences in air movement through the canopy. So that might have a minor effect, but I don't think it will be significant. But I'm not entirely sure. That's just a gut feel answer.
Radio. Well, we might pull it up there. If you have any questions that we haven't covered and more questions that you would like to, please just jot them down in an email, send them into CottonInfo or into your local regional extension officer, and we can help find some answers for you. But look, we've covered a great deal this afternoon. Thank you so much to John, Warren, Katie and Sandra for presenting today. Really appreciate your time and efforts into coming along to this webinar, and thank you to everyone for joining and contributing with such great questions. And we hope today has given you some practical tools, some new understandings, and maybe some confidence as you navigate the next heat wave event. And I guess we look forward to seeing you at the next CottonInfo event. So thanks very much, everyone.
Thanks,
See you
Janelle.
later.
Thank you.
Thank you.